Here we see the first part of our processor board is finished. There are 4 sockets in place. There are several more to go before we finish the whole of the board, but this gives an idea what it looks like. I've also included the first IC, which is a hex inverter package. That's an LS14, and that is so that we can have the oscillator running, crystal oscillator, there's the crystal, and the push button for the reset. The green LED is simply a power LED. It's not necessary to include it. I don't usually put one on, but I thought for the purpose of this project we'll show when power is applied. If we look at the other side, then we can see this is how far we've gone so far. We're using these white wiring combs. You can see the wiring has been done in several of them. This circuitry here is the reset circuitry, and this capacitor up here, there's a couple of capacitors actually, for the crystal oscillator. This shot's a little bit closer, it's easier to see, although the wires are probably rather difficult to see. Here we turn the board over and we've connected a 5-volt power supply to it, and see the LED is on. This here is a logic probe, as I'm sure you'll all recognise. What we're going to use that is for some basic tests. We should be able to check the power on the, yeah, that's plus. Note the light goes much lighter when we put it on the plus, then we put it on the minus. There you go, it should go out completely. If this, with this particular logic probe, if you have a clock signal, that's an oscillating signal, it should actually go on and off. The rate it goes on and off has nothing whatsoever to do with the speed of the clock. So that's showing it. That is actually showing there is a clock there. There's one on there. Now those 2 pins are in fact on the oscillator. They are the buffer on the other side of the oscillator. So in fact that's the oscillator one, which is pin 12. Okay. The other part we can test is the reset button. Now the reset button comes in, it's 1, 2, 3 and 4 are the pins, so 1, 2, 3, 4, so we press it on 1. That's the input to the first gate, that's inverted input of the second, there's a buffer here, and the output there. So there we go, that seems as if the reset button's working and the oscillator working. The only thing we don't know is that that is oscillating at the correct frequency. We're using a 4 megahertz crystal here. What we'll do now is we'll have a look at it on a very cheap and cheerful Chinese sourced frequency counter and see what it says. Here we go, this is our cheap and cheerful Chinese sourced frequency counter. It only has 5 digits on it, so obviously we can't show 4 and 6 noughts after it, so we have to make do with what's up there. There's also a small interface board which I had to build, which deals with analog signals as well as digital. So here we go, we have a scope probe connected up to the input of the frequency counter. If we touch it on, the output of the crystal oscillator is pin 10, 7, 8, 9, 10. We touch it on there, that's 4 megahertz. And of course the input to that buffer should also have 39999, same thing, and that's the output of the oscillator itself. Look at the input, it probably will show nothing. Yes, it's not reading correctly because we're loading it with the scope probe. Go on the output of the oscillator, and there we go. So that's it. So all seems to be well on that front. Here we have the finished board. It's finished, it's not completely finished. We've inserted some of the ICs into it. There's a few more to go yet, but the way I suggest one tests these things, because it's a good idea to test it at some point. We've already checked in the previous video, we checked that the reset button and the oscillator worked. That's checking out that part. Now what we have to do is check that the processor can speak to the EEPROM and it is running correctly. If we look at the back of it, we'll see this is now finished as much as we can up to this point. There are obviously a few wires that haven't been connected up yet on the digital to analog and analog to digital converters, because we haven't covered those bits. What we've done is put the absolute bare minimum in we can to actually make the processor run. So this is it wired up, all the data bus, address bus. This is the net list, if you remember, which we've done. What I do is I tend to put a little cross by it to show that the particular link has been done. Okay, so looking at this, putting it back again, let's talk about how we can actually check it out. Well, obviously you check out the things you can, A to B wiring and things. I like to check some of them, I don't bother to check all of them. These items we'll be putting in due course. This is a 4-segment display that goes in here. Then we have 2 EEPROMs, or the electrically erasable, so they're EEPROM. One has a very simple routine. In fact, it just consists of one instruction, one solitary instruction to show whether it is essentially working. And the second one we'll put in the display and we'll see if it writes the display. Here we have put the simple one-step EEPROM in there. Nothing else needed. This, as we've seen it before, is a logic probe. Now there's a very useful pin on the Z80, number 18, pin 18 on this side. It's called Halt, and that will halt the processor completely, and that line goes low if it encounters a halt instruction. Now a halt instruction for a Z80 is a 7.6, that's a 7.6 hex. So all we've done in this EEPROM here is we put a 7.6 in location 0. So in other words, the very first instruction that the Z80 comes upon in here, there is only one instruction, is a halt, which tells it to go to sleep effectively. It keeps refreshing memory if you have dynamic memory, but aside from that, it's gone to sleep effectively. So if we use the logic probe, we've seen this before, this is pin 18. What I'll do is I'll hold the reset button down, and if we hold it down and attach that on 18, you'll notice now that the logic probe has gone, the light has come on, in other words it's a high. Now as soon as I release my finger off the button, if it's running correctly, then that will be pulled low immediately, because Halt will go low as soon as it sees the instruction 7.6. If I let go, it's gone down. It means it must have seen a 7.6 hex instruction to be able to stop. Quite a simple way of doing it. You can see it's still low now. And that's it. That tells us that the processor is talking to the ROM. That obviously works, and we know that works. And the memory decoders and things, they're okay as well. So what we'll do next is we'll swap the EEPROM round for the other one and put the display in, and let's see if we can actually make it work. Alright, we've inserted our second EEPROM and put the display into its socket here. Now I have a power lead here, so what I'll do is I'll hold the reset button down and I'll apply some power. Now first of all, straight away we have rubbish on the display. This display does need a reset to clear all its registers, etc., and the reset's connected to the processor reset. So when we release the reset, hopefully, if it's going to work, we'll come up with something what we're expecting to see on the display. So it looks like we have something there. These little displays are quite straightforward to use, these little dot matrix ones. There's only one real instruction that's supposed to go right at the beginning. A lot of them need certain sorts of initialization, like saying what you want to do with it. This particular display just needs one instruction. Just for completeness, this in fact is the simple program we're using to display the numbers on the display when it's in their socket. These are all the instructions we use. There is actually one extra, which is just the halt instruction, but aside from that, this is the important part that gives the numbers on the display. Quickly looking through it, the first three I always leave blank. They're for no operation. They're 0 zeros in case I want to add something at a later date. The 3 is the load accumulator instructions. So first and foremost we put an O2 in. That is simply to tell the display to work at half brightness. So that's 302, the D300. 00 is the address for the whole display unit. Right, so that's the initialization done. Now we actually go to the making the display load. So we load the accumulator with a 5A, which is a capital Z, or Z if you're American. Then we output that to the display, which is D307. Now we're saying 07 because this actually is, as opposed to 00, is the control word for the display, which is the, what should we say, the setup. This is the left-hand side display is addressed as 07 in the particular way we've done it here. So in other words, we send the Z to the left hand side. Next we load the accumulator with an 8. 38 is a numeric 8. Output that to 06, so that's the next one along. 7's on the far left, 6 is the next one in. Next we load the accumulator with a 0, which is a 3-0, ASCII 3-0. Then we output that to display on 05, so we've got 07, 06, 05, and that means that's on the third one. And the very last one is load the accumulator with a 61, which is a lowercase a, and we output that D304 to 04, which is the far right hand one. And as I say, one other one at the bottom that's not on here is a 76, which is a halt. So this, it runs through really quickly and comes to a dead halt there with the halt. But that's all that's necessary to actually show that display working. With some of the other displays, like the LCD ones with the Hitachi chips, they are much more complicated to set up than this, and they need some sort of hardware fiddles if you're using a Z80 as well. These are the two decoders. If we look at the circuit, you'll find here is the display enabling line, which is from pin 12. Pin 11, 10 and 9 go nowhere. They'll eventually go to other things, but that's the I/O selector. If we look at the memory selector, it only has two options. Number one is pin 4 is going to the 2764, that's the EEPROM, and 5 is for the RAM, which we're not using. So in other words, we can straight away look, when we press the reset button, we can see that the I/O selector, because remember the program has a halt at the end, so it just runs through, shows the letters on the display and then stops. So there should be no activity at all on here after a half a second or so, after the reset button's done its thing. Likewise with the memory, it shouldn't even try and access the RAM. So let's have a look at the actual circuit and see this happening. This is the decoder, which is a 139. There are two halves to it, as I showed you on the diagram. Pin 12 is the display enable. So if we hunt around and find pin 12, we'll see what happens on it. So this is 9, 10, 11, 12. It's just showing a high. So see the light is on. So in other words, to check that this is working, that means nothing more is going out to the display, because remember, it put the figures out and then it stopped. So what we do is we press the reset button and let it go. It flashed once. Well, once in fact meant several times, but we only see it as one flicker on that. That's because it accessed the display and it is finished. So if we look at any other lines, there's another one. This would be to the D to A and A to D. Nothing. It says nothing at all. So that means that it is definitely going for the display only. If we look at the memory, just to prove we're not trying to access the RAM at all, pin 4 is the ROM. Now, interestingly enough, this should be flickering all the time. Hence, that's just accessing the program ROM. But if we look at the RAM is on 5. It's nothing. Even if we press the reset, let it go, it's nothing. Which means it's not trying to access the RAM. Essentially what we're doing here is proving that the short bit of programming we put in there is actually working. We don't need the display to see that. It just simply proves it by the fact that we're seeing the I/O, which we expect to see accessed once, or actually shows once on there, but it's several times in reality. And the memory never looks at the RAM, because there's no RAM accessing instructions in this particular program.